Guess without further ado, I will introduce John Wallace of the Society of Amateur Radio Astronomers, and he's going to talk to us a little bit about radio astronomy. Joe, go ahead. John, I'm sorry, go ahead. Unmute yourself and take it away. No, he's muted now. There.
Okay, there we go. All right, so I'm going to jump right into the presentation. Can everybody see the introduction to radio astronomy page?
Beautiful.
Yep.
Okay, great. So I am the education coordinator for SARA, which is the Society of Amateur Radio Astronomers. And we're going to talk a little bit about radio astronomy. The talk is pretty much my general talk. I know you guys are ham radio people, and I understand some of this stuff is probably stuff you know already, but I found over the years when I've gone in, there may be some ringers in there that just don't know, and I just want to make sure I get everybody up to speed. You can ask questions at the end, and of course, you can go to our website and get all kinds of information, and there's also a wonderful listserv. If you decide to try radio astronomy, which pretty much you're doing already, you may not know it, but you are, you can get on that listserv, and we have professionals from all over the world that are part of that listserv. So there is someone that can answer any question you've got because they've all been there somehow. So I'm gonna go through and we'll, let's see if this will work. There we go. So you know what radio is. Astronomy, according to NASA, is the study of stars, planets, and space. So how do you relate these two? Radio is just a different color, if you will, of light. And you can see an optical image on the left that I took from my house, and a radio image, which is from the NRAO in Green Bank, West Virginia. And you can see that they do not look the same. There are little dots up there, but there are also these funny rings and big blobs and stretched out things, nothing like what we would see with our eyes. So it's a very, very different image. And you're familiar with radios, FM, TV, all the rest. What is it? I'm just going to go through the real basics. A transmitter changes your voice, a song, or whatever is being transmitted to electricity, sends it to an antenna. The antenna radiates that signal out in all directions. Your device's antenna receives the signal and feeds the electricity to your device, and your device converts to electricity back to sound. And I have this little demonstration thing, which I'll show you just in case.
This demonstration is one I call light radio. We're going to use this to demonstrate how radios work. Here we have a battery that runs a circuit with a microphone, and the microphone actually powers this laser. So the laser beam that comes out is modulated or changed by the microphone input. Over here, we have a solar cell, photocell, that will pick up the laser light and then convert it to electricity and feed it to an amplified speaker. So let's see how this works. This demonstration is one I call,
There we go.
we've got this light radio. I'm going to speak into the speaker, turn on the laser, you can see it's on. Testing, testing, 1, 2, 3. So, radio station, feeding into a microphone, feeding into a circuit that turns it into electricity. That electricity powers an antenna. The antenna in this case is the laser, and it sends out a signal, which is the laser beam, and it would be radio waves in the real world. Our radio wave lasers hit another antenna over there, which is our photocell in this case for the laser light, and that photocell converts to electricity and feeds it into, in this case, an amplified speaker instead of our radio.
So in our terms, in terms of astronomy, we're looking at a radio source, which is our transmitter. In this case, it's Jupiter, and it feeds into a radio antenna and a receiver. And that receiver and antenna system produces a data chart, which you can see there. And then it feeds up, after you've done many, many, many charts, you can make an image. All right, so that's how it works. It's real simple. Many of these objects that emit radio signals are really far away, and so they're incredibly weak. The intensity of radio waves, we use the power that passes through an aperture of 1 meter square in 1 second with a bandwidth of 1 hertz is called a Jansky. And a Jansky is 1 × 10⁻26 watts per square meter per hertz. So it's an incredibly weak signal that we're trying to pick up. For some examples, you know, a snowflake is a milligram. It has a kinetic energy of 10⁻6 watts. So, you know, this is not a good comparison, but you know, you get the idea. A snowflake, yikes, 10⁻6, incredible. Cell phone, obviously, at a kilometer away is 10 to the 15th. 5 × 10 to the 15th joule, and a joule per second is a watt. So, you know, it's a phenomenal signal compared to what we're trying to pick up. Current radio telescopes can measure in micro Janskys. So it's pretty amazing. By the way, that's professional, not amateur. Okay. How do you gather such a weak signal? Obviously, big antennas. So the picture at the top here is the 300, I think it's 300 foot or 300 meter maybe, telescope, Green Bank telescope, fully steerable. It's the biggest fully steerable telescope in the world. Really big. So most radio objects are fairly stable. You can gather over time and usually up to days with no problem. You can observe over a large bandwidth. Most radio astronomers use 2-3 megahertz of bandwidth, maybe more. And antennas like a funnel, its depth doesn't matter. It's the opening that matters. And here's just a couple.
Here I have a piece of
induction
copper pipe, fairly thick wall
demos.
copper pipe. And I have a strong magnet and a small rock. Let me show you what happens to the rock. I'll hold it with this hand and drop it through, and bam, really fast. Drops through very fast. Let me do it again. Bam. All right. Now, what happens when I drop a magnet that passes through? Now, just to show you, it does fit. There is not a friction or anything like that. It's just floating down. And here we go. A lot longer to go through. What is going on here? This is something we call induction. The magnetic field lines travel through the copper. Copper is a conductor. And so those magnetic field lines produce electricity. And that electricity in the pipe makes magnetic field as well. And it turns out it pushes against this magnet. And the stronger the magnet, the stronger the push back. So the slower the magnet would fall. This is a very strong magnet. And so it drops very slowly. Now we're going to look at induction again. This time we're going to use loop antennas. And we have here just a regular old portable AM FM radio. And I have a station on here. And you can hear there's a signal coming out of that. So I'm going to plug the antenna into that earplug. And over here I have our amplified speaker again with another loop over here. And you can see these loops are just round coils of magnet wire. And let's turn this on.
Brought to you by Sweet Dreams Home Furnishing.
Noticing, I hope that I am not touching the lower magnet, the lower coil. And yet we're getting a signal. So the electromagnetic radiation is going through that other coil and inducing a current through it, which is going in and making the sound. I can also show you one more thing, which really doesn't have to do with this, but it's called polarization. When I hold the loops parallel to each other, I get a large signal. And when I turn it sideways, notice how it gets quieter and quieter and quieter until it's almost zero. That's called polarization.
Okay, so the electromagnetic spectrum, just really quickly, it's we mentioned radio is just a form of light, and that's the electromagnetic spectrum. Electric charge changes speed and direction. It gives off electromagnetic waves, and how fast those waves wiggle determines the kind of electromagnetic radiation created. If you have nuclear transitions, you're up in the gamma ray region. If you have oscillating charges, you're in the radio regime, and in between, there's all kinds of other atomic and molecular things that go on. And in terms of sizes and stuff, this chart really shows it all. I really like this chart because it shows that radio is huge. You got size of a soccer field up to a baseball, and this one is drawn fairly much to scale, except the visible light should be as thin as a pencil line on this. Visible light is just ridiculously small part of the spectrum. If you notice, radio and microwaves, which I consider radio, actually go way up. And, you know, it's a huge part of the spectrum, and it's a part that we don't give enough credit to in astronomy, even though we've learned a lot from it. So there's that spectrum. And what can we see with it? So if we look, depending on the radiation that's coming out, in order to get to the top, you need higher and higher energies, which means those objects are hot. Okay, so basically we can think of this as a temperature graph. The things at the bottom are really cold. A cosmic background is 2.7 Kelvin. So it's pretty darn cold, minus 400 and whatever degrees. And then it works its way up into black holes and supernovas, which are unbelievably hot. All right, so you've got, you know, us at infrared, we don't give off light. You turn off the light, you don't glow in the dark. So we give off infrared. Visible, you can see the galaxies and stars and sun, all the things in astronomy that we're used to looking at. And then these other ones, you get to see the oddball things that we can't see with our eyes, black holes, supernovas. And the thing you got to remember is that anything that gives off heat gives off some kind of radio radiation. So all of these objects are visible with radio, every single one. All right, and a quick infrared.
We have our photo cell and amplified speaker back again. And here is a regular old remote control. If I shine it at the camera, you'll notice you don't see anything. And yet radiation is coming out of here. Infrared radiation, we can't see. But this sensor can detect it. To our ears, they all sound the same. But if you ran this signal through an oscilloscope or something that could capture very fast what's happening, you would see different wave patterns that these infrared signals are actually making. And that's how the TV or remote control device knows what you're pressing. We have.
Okay, so here's some images just to give you an idea of the different electromagnetic frequencies and what we can see with them. So radio is good for seeing through dust at different things out there. And you see it looks, these images, by the way, you can think of as you've got the entire sky as a globe surrounding you, and you're at the very center. And what you're doing, it like the maps in your old schoolroom from when you were in grammar school or elementary school, they peel that globe open and make an oval, right? And so that's what we're doing. We're taking that three-dimensional sphere that's surrounding you, ripping it open and slapping it into an oval with the Milky Way galaxy through the middle. So you see the radio frequencies right here, and that's the Milky Way. And you've got these loops here, which are coming up. Lots of dust and things like that might be triggering that. There's interstellar dust and stuff. This one is different. You can see it's got this thing going like this S-shaped thing. This, remember, this side is related to this side. They're actually touching. So this is actually a loop. And it turns out that's our solar system. That's the interplanetary dust. So infrared can pick up dust, visible light, X-rays, and gamma rays. And they look totally different. So using different frequencies gives us different information. And another reason for studying radio astronomy, if you look, all the things in the energetic realm are blocked, completely attenuated by our atmosphere. Visible light, again, a very thin line, not this big fat thing, but it would be a thin slice is attenuated. It is not perfect. That's why they put observatories at the top of mountains. And then there's some infrared things that get down pretty good. If you're at the top of a mountain, you get some results. But then look at this huge swath with zero attenuation, right? Comes all the way through, no blockage whatsoever. So this is why radio astronomy is actually preferred by many people, because there is no blocking. There is no atmospheric problem. All right, and that's why we see Keck Observatory, which has some infrared observatories, has to be at the top of Mauna Loa. And then the radio telescopes are generally in valleys, and that's to protect from all the human-made garbage that's being transmitted nearby. If you've never been to Green Bank, West Virginia, which is where the observatories are, the biggest ones, it's got a 50 square mile patch of land around it that is radio quiet, which is bizarre. You drive in and your radio goes dead, cell phones go dead, everything goes dead. They even have a truck that drives around and looks for electric blankets and things like that. They give off radio signals. They can detect all that stuff. So people that live in that 50 square miles have to actually, participate in removing all the cell things that they've got, the radio signal things that they've got, so that the observatory can actually observe. So it's kind of an unusual place. If you've never been and never experienced that, it's bizarre. Advantages, anything that gives off heat, like I said, we can pick up with radio. Electronically combining radio telescopes all over the world. Right now, interferometry is the thing, and that's how that big event horizon picture that they came out with of the black hole and galaxy M87. They made it by combining radio telescopes to make an Earth-size radio telescope, and they got down to microseconds. So a milliarc second, just to give you an idea, is a hair width at 10 miles. That's the resolving power. It's pretty incredible. Radios can see through most clouds of gas and dust. You can see the inner parts of galaxies and nebulas. That's why we could capture that black hole, the event horizon around the black hole. And it's relatively inexpensive compared to other telescopes. This picture down the bottom shows the Atacama Large Millimeter Submillimeter Array, ALMA, which now has, I believe, 66 12-meter dishes. And it costs less than one big telescope, optical telescope. So they can do phenomenal things down there. It's a really amazing facility. And here's some images taken with radio telescopes and other telescopes. But one of the things I want to bring up is 65% of our current knowledge of the universe came from radio astronomy. Almost nobody knows that. And it's really a shame, because a lot of this stuff is, on TV and stuff, and they just don't point it out. The Vela pulsar, Cygnus A, which is a radio galaxy, and you can see the different frequencies, what they give us. So X-ray, the blue, and then radio, you wouldn't see the jets unless you had the radio. Cosmic background, you can't detect without radio. The center of our own galaxy. This picture here is a very small section of the very center of our galaxy, and the black hole Sagittarius A star is right there. And then here's that black hole event horizon that was captured in M87. So it's incredible the amount of stuff that we've done, and almost nobody knows. So there's several ways of generating radio emissions. Black body radiation, it's the radiation given off by an object related to its temperature. The lower the temperature, the lower the energy or frequency of that radiation. And a black body, you probably all know this, absorbs all the radiation that falls on it. And it turns out most objects in the universe behave this way. So if you look at the curves here, you see at a certain temperature, like 6,000 Kelvin, it's in the yellow. And guess what? Our sun is 6,000 Kelvin. So its peak is at yellow, and that's why it appears yellowish. All right. The other thing that happens with this is these lines do not overlap. So if you have a very carefully calibrated radio telescope and you get a measurement, you can actually determine the temperature of that object very accurately. So that's another thing you can do with this. All right, here's an example. Here's a beautiful optical image of Saturn. It's beautiful. You can see clouds and things like that, but it's all reflected light. We're learning nothing about what's going on inside Saturn with that image. But in the bottom image, it's a radio image, and it shows that the rings are very cool, and the planet itself came out to be 100 Kelvin, which is much warmer than it should be. And scientists are now suggesting that maybe it's still contracting, and that process is causing the warmer temperatures. Spectral line thermal radiation is another emission thing. This is the one most radio astronomers use. It's the hydrogen spin flip. Basically what happens is the electron switches direction that it's spinning, and that gives us 21 centimeter wavelength or 1420 megahertz signal that's emitted. All right, and so this is one of the ways we get spectral images using radio astronomy, so we can identify atoms and molecules. And there are thousands of atoms and molecules that have been identified with radio astronomy. So just a few of the important lines here. You know, the hydrogen line I already showed you here at 1420 megahertz. There's one at 1667. There's actually several for hydroxyl right around 1667. But this is called the water hole, and this is where the SETI people look because they think that's significant. Water is up here, oxygen, things like that. So down below, you can see the optical spectroscopy things. Some of you may remember doing that with prisms and stuff back in science classes. And I want to show you a short demonstration of that using just very simple things. This is a light bulb. I'm going to rip through this because I'm sure many of you know it. So I'm just going to fast forward. I'm going to fast forward. Let's see. Somewhere in, oh, no. All right.
About 50 cents, I think.
So this is a diffraction grating I'm using from Rainbow Symphony. It's about 50 cents. It does the same thing as a prism. Where is it? Okay.
And as I turn, because it's like a prism, you have to turn 60 degrees away. You'll see we go through violet and blues, and the yellows and the greens are being washed out by the camera, and red. But if you're able to see it with your eye, it's a beautiful continuous spectrum, just like a rainbow. Beautiful. Okay, let's go back and look at an element now. Compact fluorescent bulbs have mercury in them. And so in this case, we're going to have to turn this way. And we're starting to see the spectrum. And you can see it goes, there are some bright lines there. You can probably see them. They're red and a yellow and a green and a blue. They're being unfortunately washed out by the sensor here, but you can sort of see that there are at least bright lines in that spectrum. Last, let's look at neon. In this case, the neon is a very small object, and we will go this way. Oops. There it is. You can see a little line there with some red and oranges and yellows. Next.
Okay, so if you get a chance to see it with a real grating, it really is quite dynamic. The camera really messed that up. But there are other ways of generating electromagnetic radiation that like radio waves, and that's non-thermal methods. So we're going to look at two, synchrotron and masers. And synchrotron radiation, you have a strong magnetic field and you have charged particles, a proton or electron that's spinning around, and that generates radio signals. You get really energetic things like supernova remnants, black holes, neutron stars, and pulsars, active galactic nuclei, the black hole in our galaxy. Jupiter gives off synchrotron radiation. So if you've ever detected the signal from Jupiter, which you may have, it's in the decameter range, you are detecting synchrotron radiation. Okay, and here's some synchrotron radiation pictures. you can see here why why radio is important. Here's an X-ray picture in color that looks like one galaxy. But when you look at the radio signals, you see the shock wave features that show that it was actually two galaxies that merged. Here's the Jupiter picture using the VLA, which is that huge radio telescope, so they can actually get these beautiful images of the magnetic field lines with the synchrotron radiation, and then a VLA image showing some gas jets shooting out of a quasar. Non-thermal radiation, again, could include masers. You know what a laser is? A maser was just the radio version, and it was discovered long before lasers. And so you look at molecules like water. This one over here uses hydroxyl OH, and this one here is looking at water. These are very weak signals, but because they're masers, they're able to get greatly amplified, and we can actually see these objects even though we technically should not be able to. So it's because of these masers that we're able to see it. A little history, Karl Jansky, you may or may not have heard of him. He worked for Bell Labs back in the 30s, early 30s, looking at the shortwave radio, which was used as telephone calls for overseas, 10 to 20 megahertz. It was very expensive and the sound quality was pretty bad. And so they wanted to try and improve it. So he looked, and after several months, he found there were three types of static: nearby thunderstorm, distant thunderstorms, and a faint hiss of unknown origin. I think his antenna is really bizarre looking, this thing here, and it was fully steerable, so it turns. It was destroyed by Bell Labs after he was done with his research. They took it all apart, but there's a model of it at Green Bank, and they actually had it, last time I was there, which was a few years ago, they had it hooked up so you could actually hook up a radio receiver to, a radio telescope to it and use it to detect signals. So it still works, which is pretty cool. Anyways, he spent a year investigating that third type and eventually found that it was the Milky Way. And this was widely publicized, May 5th, 1933. It made it into the New York Times here. Jansky wanted to follow up on it. Bell Labs didn't, and that was that. And so radio astronomy almost died, but along comes an amateur, Grote Reber, who was actually an avid ham radio operator, and he wanted to explore this. In 1932, Karl Jansky discovered these things. He wanted to do it, and then so in 1937, he built a parabolic dish, and I believe he built the first parabolic dish to be used in this way. And so a parabolic dish is great because it focuses all the waves, any wavelengths, to the same point. So it's perfect. I can't imagine what it would be like here. I mean, if you look at this picture, these are people. That's a big antenna. I think it would be like Noah and the Ark. If you look next door and said, "What are you building over there, Grote?" That's pretty big to be in your backyard. But anyways, he built it. This stuff, by the way, is in Green Bank as well. This radio and his equipment he donated. He actually was living in Tasmania, and he came over special and donated it a couple of decades ago. Anyways, he thought it was thermal, and so he started at 3,300 megahertz, then down to 910, failed. He went down all the way down to 160, and he finally detected something. And it turns out these emissions are not thermal. They're synchrotron radiation, like I said, black hole in the center. They didn't know that back then, of course. And so from 38 to 43, he made these observations. And if you look at these curves, these peaks are the Milky Way going through, but you notice all these hairs sticking out. Back then, spark plugs on cars were unbelievably noisy. You can see one here, which must have been made during the daytime. It looks like it's got a beard. It's just incredible. So the amount of noise it makes is just incredible. But he made the first maps. These are some of his maps of objects, and it ensured radio astronomy's future. So radio versus optical. If you're into photography at all, you know this stuff. CCDs and CMOS cameras, millions of pixels or dots to represent the data. Photodiodes collect the energy, convert it to voltages, downloaded by row and column, and you can reconstruct the image. And here's an optical image. You're pulling way in to see those pixels, And it looks pretty good, you know, at normal magnification, but way up you can see it's made up of little squares. And here's some optical images. I do some stacking photography for astronomy as well. And it's just incredible what you can do with these cameras nowadays. And so each image you're capturing is millions of dots, and you're collecting hundreds and hundreds of images within seconds. And then you get to radio astronomy. Radio telescopes collect 1 pixel at a time. And it's a composite for sure of many data collections, and it can take hours, days, or in my case, my first radio telescope, it took 10 years. So it can take a while. Here's an image from one of my scans from my first radio telescope back in the 80s. It took me 10 years to build because I didn't know anything about radio. And so I had a big steep curve, and starting out with a drift scan 1420 total power radio was really difficult. And there were, at the time, these are not things that you could buy off the shelf. In the 80s, you had to make things. So I did 1 pixel every 10 seconds. That's what it's called, the integration time. And this is a 24-hour scan. And you can see the center of the galaxy is right here where that arrow is. And when you do multiple altitudes, I had to do altitudes because I couldn't point south, but altitudes, and then you can figure it out. I went from 25 to 70 with my radio telescope every 5 degrees, and I did 10 scans for each one. So it took me 10 years to make this image here. So year 2000, I found Mathematica was the only thing I could find that handled this much information. Back then, this was a full hard drive full of information back then. It was a tremendous amount of information. And so this is a 3-dimensional. And here is a modern professional image. And you'll notice it's got the same big spike. There's even this depression here. So, you know, for a backyard from the 80s, not too bad. I was pretty pleased. So these are some professional images, pretty amazing. Radio galaxies and things like that, the center of the galaxy we already talked about. And so it's pretty incredible. Professional radio telescopes, the Green Bank scope I mentioned is the largest fully steerable in the world. Arecibo, unfortunately, I'm sure you've read the news, catastrophic failure, 2 of them. The first one did some damage to one of the pylons, and then the second one took this thing down onto the dish and it totally destroyed it. So it's gone, which is really a shame. ALMA, we talked about, huge interferometry setup, and they've got them positioned around so they can get these streaks that fill in the dish. So the more radio telescopes you have spread out over the size of the area you want to gather information from, the more information you can collect. This bizarre looking thing that looks like, you know, pipes cut open with a long antenna through the middle is called chime, and it was specifically made to try and understand these fast radio burst objects that we're finding that are on the order of milliseconds. So they've detected many of them, and it was relatively cheap to build. And then the VLA in New Mexico, this Y-shaped arrangement, and they can spread that out using railroad tracks. These are 27-meter. Each one is a 27-meter radio telescope. It's pretty spectacular. So this is something that you may see something like this somewhere else, but I put this together. You know, SLF, you got Whistler radio. I'm going to talk about these individually, but Whistler radios, VLF radios for things like sudden ionospheric disturbance, solar stuff. Jupiter and solar stuff can be studied 18 to 30 megahertz, which is in the decameter range. And you guys may have actually detected some of these already. FM meteor detection I used to do, you know, with my students. And I'm sure you guys have done meteor signal bouncing and things like that. Continuing drift scans, 406 megahertz is big with radio astronomers. I'm not quite sure why that frequency, but 1420 is the hydrogen line. We talked about the spin flip, and then 1667 for hydroxyl. And then We can also do Doppler shift stuff, and that's something I'm going to talk about. My newest projects are in Doppler shift, and you can study regions of our own galaxy. And then up in the gigahertz ranges, you can do extraterrestrial satellites like Cassini and the Venus probe and Planck and stuff like that. A lot of people pick those up in the radio astronomy community. And then I have a little demonstration radio telescope I take around with me to all my observations to let people learn a little bit about radio, because you'd be surprised how little normal people know. My talk here would be overwhelming for most most normal, quote unquote, people. All right, so let's go through. Whistler radios are one of my favorites. Very low frequency. They're looking at lightning, aurora, solar flares, other effects that are felt on Earth and the atmosphere. And they're great because it sounds like something. You know, they have that scene in Contact with Jodie Foster with the headphones. She would have been listening to the static. I mean, come on. There's no need for the headphones. You're not going to be able to tell the difference using your headphones. But these, you could tell. These are spectacular. They look at signals traveling along magnetic field lines, and those magnetic field lines from the Earth go out 3 times the diameter of the Earth. So they really go long distances back and forth, and you get dispersion. So you get something that sounds like a bomb dropping, and that's called a whistler. So it's really amazing stuff. And they're relatively easy and cheap to get, 10 to 10,000 hertz. The problem with this is 60 hertz is right in there. And if you're anywhere near electricity, like I can't do it in my house because it sounds like this loud buzz everywhere. So you have to wait for a power outage, or you go way out in the woods. I used to try and get, when I was doing it a lot, I used to try and get at least a quarter mile away from any electric lines. And that's really hard to do nowadays. But it's really spectacular to listen to. So there's 4 basic things. There's a bunch of other things you can listen to. There are very strange effects that you can pick up. You can pick up insect wing vibrations. I'm not sure why, nobody's explained that to me, but you can actually hear flies buzzing around the antenna, which is bizarre. Anyway, spherics is the first one. That's your local lightning. You've all heard that. It's the noise that you get on AM radio and sometimes on other radios. Tweaks are more musical. They're lightning that's far away, up to 1,000 miles away. And they're sort of, the closest thing I can come to is like a musical saw, kind of a twang. Whistlers are the bomb dropping thing. And that's where they've gone from one node on Earth to another, back across through those magnetic field lines. So they're traveling huge distances and being dispersed. And then chorus, I've detected many times, and it sounds like crickets chirping or birds. It's the charged particles from the sun being pulled toward the poles, and that's most times it's what causes the aurora. There's a few other things that cause aurora, but these recordings I'm going to be playing are from Steve McGreevy. He's out in Colorado, and he gets up into the mountains and can really make some phenomenal things. I'm going to play that one more time. The tweak is the best tweak is at the very beginning. Hear that little musical note? And it, okay, so VLF Solar Radios, I built one from AAVSO many years ago, this one here. And you're looking at the sun's impact on Earth. So you're looking at solar flares and how they impact the ionosphere. The radio station I was using at this time was in Cutler, Maine, and I live in Maine now, and drove over and got this image down here of the antenna. It's a huge thing, absolutely phenomenally large. This is way far away. I couldn't get anywhere near it. It's a restricted area, but it's a spectacular thing. And I turn in my data to the American Association of Variable Star Observers because the sun is a variable star. And so they use the data to study the sun and its activity. And flares are tremendous outbursts of energy from the sun. A 20-minute flare, just to give you an idea, current energy use of the US it would run for 100,000 years on 20 minutes of flare activity. So tremendous bursts of energy. And these affect the D, E, and F layers. And you've probably experienced communication problems when one of these big flares happens. They're categorized A, B, C, M, and X. I have no idea why M and X, but that's the way it is. They're factors of 10 and they're open-ended at both ends. So X flares can go way up in number. Right now I'm using something called a super SID developed by Stanford. Here it is, the size of a tuna can. It plugs into a sound card. It's got to be 96 kilohertz, but it's any sound card. It has to be run on a desktop. Laptops are way too noisy. And then it's got 400 feet of wire on, this is a 1 meter thing, but you can make it larger if you want, so it sounds better, more detection. And they give you a screen that shows the frequency versus time. So you're getting a spectral view. And here's the 24 kilohertz for Maine, Cutler, Maine. And this is NML. These are all submarine communication things. It's designed to be able to penetrate water. The low frequency penetrates water better. So they're tremendously powerful and, you know, really cool devices. Anyways, so these, Sarah took over the production of these and we've distributed to hundreds of schools all over the place, mostly overseas, believe it or not. And that's because overseas, this may be the only scientific instrument they have at all. And so there's a big push to use it. Whereas in the United States, kids are lucky and they have you know, resources that are unbelievable. And so a solar radio is like put on the shelf and used maybe once a week, once a year or something like that for a couple of days. So it's a tremendous out of the United States. And there are a few groups in the United States that do a few things, but not much. And so it's a little disappointing for us. But, you know, like I said, radio, we're trying hard to push to get people to understand what radio can do. So the charts, you see this peak at the beginning, you see a peak at the end. This is sunrise effect, sunset effect, and in between, you know, the sun goes across the sky and you get this sort of curve. And there's nothing happening there, no flares. Here's a day with some pretty powerful flares. You've got the sunrise effect here. You've got a C flare, a really powerful C flare. You got a weak C flare right here, and then a big M flare right there. And this is the biggest flare I ever detected on the 15th of April in 2001. It actually peaked my radio. I was in a spot where it had I was at a nodal point, and so instead of going up, the signal went down. So I had inverse signals, but so this thing bounced up, and you notice it took about 9 hours to recover. That was one heck of a flare. All right, so total power radios. This is my first radio, and it's designed for just picking up 1420 megahertz, no spectral. And here it is. It took me 10 years to get this thing in a working order. I had to put everything in a cooler, and I had kept it temperature constant. And you know, you got a little antenna here, a little can with a rod sticking up. That's my antenna coming down, really good cable into this thing. So I would set up and take measurements using this. And like I said, after 10 years, I was able to make this picture. My newest one is using SDRs, software-defined radios. The entire system cost less than $300, not counting the laptop. My first one I showed you there was well over $2,000. And this little cheap SDR, which was a real cheapie, it's one of the cheap ones, 30 bucks, I think. It does so much more than my other one could. So it's incredible. The technology has really come a long way. So I've got a horn here. You can see this is all pretty portable. So I can fit this in my car, just barely, but I can fit it. It's got 2 low noise amplifiers. It's got a bandpass filter. I wanted to get rid of some, you know, cut down the frequency that's passing through. I had a lot of problems with some FM, so I put an FM trap in. And the cheap SDR tuner slips into the laptop and it runs some software and a power supply and bango, you're done. So with this horn, it's too small to detect individual objects. My first antenna that I showed you was huge. It was a 10-foot antenna. I could resolve images and I could go down to 50 Janskys with that. The horn antenna is small, so no individual objects. I can't pick them up, but you can go and pick up the increase in hydrogen gas in the Milky Way, and you can map that. And so I used galactic longitudes. If you look at this little chart here, here's the sun where my little pointer is, and that's 0 pointing toward the center, 30, 60, 90, all the way around 360, right? So that's the galactic longitudes when I talk about it. So I found that I could do all these 5 projects, and I had never seen anybody do all 5 at once, so I decided to try it. And I was able to do it all with pretty much one set of data. So 24-hour scans of the sky, galactic longitude graphs. I then was able to use some numbers and calculations to be able to get rid of the movement of the Earth and the sun and things like that, and come up with something that's called the local standard of rest velocity, which is the actual speed or velocity it's moving in the galaxy, and then create a galactic rotation graph and then a galactic arms graphic. And I'll show you each of these. These are the 24-hour scans. And here we've got the 0 line is no movement. You got red shift and blue shift. And you can see these things are weaving in and out. It's really cool to see, you know, moving toward us and away from us, you know, or I guess it's away from us and towards us. So it's kind of bizarre to see all this movement when you're used to seeing static graphs, but it's fascinating to study. And you can actually figure out the speeds that these things are going. So this is the galactic longitude graphs, and these are different elevations. This horn antenna had a really big beam width, so I did 30-degree increments. So I went from 30 to 60 to 90 to up to 240. And these are the different graphs I was able to create. The SDR, by the way, has a absolutely horrible bandpass. And so I had to take and point the, you notice it says corrected with a concrete baseline. So what I did is I took the horn, pointed it at concrete, and got a graph. And I took that and subtracted that from all my data. And that's how I was able to detect these things very clearly. So the SDR that I was using, this little cheap $30 one, really is not great, but it's able to do some stuff if you get rid of the background garbage. So here's the graphs, and you can see they're spread way out. There's lines here and way over here. And, that's really, if that were true, these things would be flying around. But when you take the movement of the sun and the earth out, everything snaps back toward the center. Here's the 0 line right here. And most things are pretty close. You got some things red shifted, you got a few things blue shifted, and you've got some lines way out there that are, pretty far blue shifted. So the next thing I did was figure out the galactic rotation. Kepler came up with the idea that as things got farther away in the galaxy, they would go slower and slower and slower and slower. And so the galaxy should be following this red curve. But guess what? When the professionals went out and measured it, it follows this blue one. And these 3 green dots are my data. You have to do it between 0 and 90 degrees, and I only had 3 dots that I could use. So, but you notice it's pretty close to the blue line, considering it's a $300 radio telescope compared to the tens of thousands for that professional line. Not too bad. It's in the ballpark. And then the last thing I did was create a galactic arms graphic. And you'll notice these dots, these stars are my measurements, and they're in the ballpark. They're pretty close. There's a few that are a little bit, that's a little too close to us. It should be a little farther, but yeah, a $300 radio telescope, I think it's pretty good. And I wanted to talk about some other projects. Radio Jove, I mentioned decameter radio. We do a lot of these with foreign schools too. I believe this is India. And it started with NASA, and then we're now part of helping them out too. The NASA people retired and they're doing it, but we're helping them out. And so we send a lot of these overseas as well, and we have some in the United States. It's looking at the frequency range for Jupiter noise is 15 to 38. Generally, they pick around 20.1 because you can tune down to 20 to make sure you're getting a signal. You know, WWV is really powerful at 20. So you can tune out to 20.1 and start detecting. And there is a little tuning ability so that if there's a noise source near you, you can tune a little bit away from it. I was asked to help proof this years and years ago. NASA sent me one, but I didn't realize that these are 25 feet apart. They're dual dipoles, and they have to be 25 feet apart on all sides. And I was teaching inner city, and I lived in the city. So it was like, where are you going to find a 25 foot by 25 foot place to put it? And I couldn't, so I sent it back. But it's a really cool thing. If you've listened to Jupiter at all, you know there are two basic sounds you can hear easily. The long waves, which sound like waves crashing on the beach, and the S waves, which sounds like popcorn popping. And here's the L bursts. Can you hear that at all? Yeah, okay, cool. And then the S bursts are easier to hear. Okay, you can also pick up the sun with these radio Jove, and there are actually 7 different types of solar type of radiation you can pick up. Solar flare activity, 7 different types. This is little shark fins again, you know, that goes along, and then all of a sudden increase, and then down quickly. I'm going to play just a little bit because it gets pretty loud, and I'm just going to turn it off. So let's get that back. Okay, so meteor detection, I am betting that a bunch of you have done this, you know, signal bouncing off the meteors. SDR radios are great for this. I have one. I haven't recorded it, but it's great to go out during a meteor shower because you can't see a lot of the stuff that's hitting the atmosphere, and you can pick it up. So I'm picking up probably 10 times as much as I'm seeing. So it's pretty amazing. So, you know, the past shower, I think they were saying there was something like 60 per hour. I was picking up 10 times that. It's pretty amazing. So anyways, I'll play us this sample. You'll hear the radio station go in and out. This was 102.1, so it's a FM station, and it was done by Jadrell Bank. So it's, you know, you can pick that up. Gamma ray bursts, I tried this. You're supposed to be able to pick it up on low VLF. I didn't have any luck. And you can see here, here's a VLF thing, and then a gamma ray burst happens, and you get this massive dropout. I didn't find any correlation on my charts, but there are some people who are trying this, and it'd be cool if we could get it, because then we might be able to pick out where these things are coming from. And pulsars, this is big now in our club. There's several people that have done this. There's one guy in Australia that actually beat the professionals, and Vela Pulsar, which is the one I'm going to play you, is really powerful and for a pulsar. And it goes through this weird thing where it changes frequency slightly and then comes back. It's got this little burp, if you will. I forget what the actual term is, but it's like this little defect, and he picked it up and mentioned it, and they went back to look at their data, and oh my God, there it is. And so he got you know, accolades for that. But I'll play this. It's changed, the speed has changed, so we can hear it. It's 0.089 seconds, which is really short. So this is slowed way down. But that's a pulsar, which is giving off a signal. And those are used a lot for timing. They're really accurate in most cases. And interferometry is the way we're doing it now. Most professionals are doing it. I'm not doing it that way, but professionals, I've done it a couple times. You get these fringes because of the interference patterns. And you can adjust your radio telescopes all around so you can have different distances all over the place and fill different requirements. So if you have it really wide, you can see really tiny detail. And if you have it close, you can see the broad picture. So you can get all kinds of views by using dozens, or like I said, ALMA has 66. If you use 66 radio telescopes spread out in particular ways, you can cover the entire range of what you could view. The problem is you have to sync to atomic clocks, which is 10 to the minus 15 seconds. So it's really tough to do. And you'll see interferometry gave us this image, the event horizon. And they're working right now on interpreting the one from, they did our galaxy too, but it's very complex for our galaxy and they haven't published anything yet. So questions. I do want to mention, by the way, that Sarah has just, and I mean just this week, we tested a radio telescope, a simple one, an SDR kit, and we're selling it for $295 with everything. You get it shipped to your house with all the software and everything else and directions. And it's, you know, I haven't used it myself. Several people have tried it to make sure it works and everything. It's based on something that was on the RTL SDR site, and you can check it out. There's a link on our webpage here. If you scroll down the home page on the right-hand side, there's a bright red thing that says scope in a box, I think is what they're calling it. So you can click on that and it links you to the article where they got their inspiration. And so if you're interested and want to see how it's done, that's one way. There's also an article that I wrote on the radioastronomy.org. The 5 projects that I showed you the final graphics for, I go through step by step in the article. And so I think it's called First Experiences. So if you put Sarah Radio First Experiences, it'll take you right to it. It's under the education page too. So you can find it there. But I want to open it up if there are any questions.
You guys can unmute yourselves. It's a small enough group, or you can just press and hold your space bar to temporarily unmute and ask a question.
Okay, John, when you were talking about Project Jove, I believe it was, you were talking about things in the 15 to 38 megahertz range, which include like or are near 12, 15, 17, and 20 meter amateur bands.
Right, exactly. That's why I figured you guys have probably detected this stuff.
Yeah.
A lot of ham radio people that I talk with say they've already, you know, heard these things. They get these funny signals every once in a while, and they were wondering what they were. And that's what it is. You're picking up Jupiter. There are programs that have been written, by the way. There's a guy, Jim Sky. He has a site called Radio Sky Publishing, I think it is. And he has a program that predicts, it's cheap too. I think it's like 20 bucks, but it predicts pretty close to when the events are going to happen within an hour or two. So you set up a couple hours in advance and you can detect these things if you want to. So you could use your own ham equipment. I think it was Ken that was talking about it, right? You could use your own equipment. You might need a bigger antenna, but you know, you probably have enough expertise in that frequency range to be able to design something that would be able to detect it. We use it for the Radio Jove. We use that, like I said, the 25-foot long dual dipole to pick it up. But there are lots of people using helixes. I know somebody that has a quad Yagi that he uses. And he actually discovered a new type of radiation coming from Jupiter. The professional researchers actually showed up at our meeting one year so they could hear about his discovery, because they had never seen anything like it before. So it was pretty fascinating. An amateur, you know, contributing to professional research. But did I cover what you were asking?
Yes, you did. Thank you.
Okay, great. Yep.
Hi, John. How you doing? I'm Scott. Thank you so much for such a great presentation. It was really informative.
Okay, thanks.
I'm a total beginner. I'm a ham radio novice.
Yep.
And I have a question that is not entirely related to radio astronomy, but either you or someone from Limemark could help wrap my head around this. I've been thinking about the differences between sound waves and radio waves, and I'm trying to understand. The ear can hear sound waves due to the jiggling of air molecules, and that's how we are able to pick up audio signals and hear sound waves. But the ear is unable to hear radio waves. And I'm trying to understand, what is the process by which audio signals can get attached to radio waves, right? I was looking at when you showed us your demonstration with the laser, and you speaking into the microphone, and the laser was going to the cell, and the cell was connected to the speaker. It made me think about, how can radio waves carry audio signals? Like, what's the process by which radio waves can carry it?
So basically the difference between sound and radio, there's a couple things. First of all, sound is generated by motion of matter. So you need substance. If you're in a vacuum, there is no sound. Star Wars would be really boring if they did real science, because each explosion would be silent.
Right.
Real boring. So, all those things. So without matter, you have no sound. So, and there are a couple other things. Sound is moves back and forth. Molecules move back and forth, whereas light, they move up and down. The speed is totally different. 1,100 feet a second for sound, 186,000 miles per second for light. Or any electromagnetic radiation. The thing I was showing there with the light changing to sound, what's happening is it's hitting a device that can take that light energy and convert it to electricity. And so it was the electricity that was being changed to sound. The way the light was transmitting that information was, it was modulated. And modulated means, different waveforms. So by speaking into that speaker, the sound waveform was changed to an electric waveform that matched it, and then transmitted by that radio, by that light source. So that's how radio signals are transmitted, TV, all that stuff. It's transmitting changing a sound, if you will, into an electrical waveform that can be transmitted long distance at high speed. And that's pretty much it. I hope does that clarify it a little bit?
Like a telephone handset, right? Isn't that what a telephone handset does?
Yeah, they actually use little quartz crystals in there to change the electric signal back into sound. It vibrates at a specific frequency, right?
I see. Okay, thank you.
Yeah, sure. Yep.
Question?
This is Gary at W2MIT. I was very disappointed to see what happened to the Arecibo telescope, because I had been analyzing data from that for years, right? I was a participant in the SETI at Home project at Berkeley. And did they ever collaborate with you on that kind of stuff?
Well, we had speakers that have come up from Arecibo. I mean, we were devastated when we got the news. There were so many people on our little listserv that were trying to figure out when the first one happened, how to fix it. We have a lot of engineers, and so they were saying, "Oh, we could go in and do this, that, and the other thing. We could do that," and then it just collapsed. And it was like, "Oh my God!" And one of the things that There are several things about Arecibo that are special. First of all, it was huge. It's not the biggest anymore. China built one bigger, but it's so iconic. It used radar. It was one of the few things that could actually radar images. So we got images of close coming asteroids and things like that. We could use it. It was an incredible tourist draw for Puerto Rico. It kept Puerto Rico in business pretty much. And so they're really devastated. They don't know what they're going to do. And the NSF is trying to find ways to build things there that could be replacement kind of projects, but it's not Arecibo. And, getting that iconic image of like Jodie Foster at Arecibo and stuff, everybody is like, oh my God, you're right. It's iconic. And it's just a piece of history that is, for those of us of age, it's just devastating. And, to me, when I saw it, I was in tears for a little while, because it was just, oh my God, it was one of the ones I really wanted to go to. And I says, I'm going. And then all of a sudden, wham, it's not there anymore. It's like, oh, because I've been to many of the others, and it's just, yeah, you're right. It's overwhelming. The amount of stuff that you should check out what they actually were involved in. It's just incredible, the amount of research they did. And so it's a great loss to the astronomical community. There's nothing else on Earth like it, and never will be again, probably.
John, do you think that it might be reasonable to put an array of smaller dishes inside the bowl of the original dish to
They
sort
could,
of simulate it?
but it still would not do what Arecibo could do. It would be a solution for getting something done, but it wouldn't do the things that Arecibo was designed to do. A lot of the radar stuff, you need a big giant dish to get the resolving power. And with radar, you can't use multiple dishes easily. So yeah, I mean, that's one of the things they're looking at. I know NSF is in the process of trying to find something that won't wipe them out, that they could put down there that would be a draw, because Puerto Rico is just devastated. Scientists that are stationed there are just devastated, and they're trying to come up with some solution for what might fill some of the slot that's there. And I'm sure interferometry is going to be part of that, because that's the big thing.
Well, I guess it would be monumentally too expensive to just rebuild it.
Oh God, yeah. Yeah. Oh my gosh. It would be billions of dollars, and they're not going to spend that. NSF doesn't have that kind of funding to kick around anymore.
Comment about Arecibo.
Yep.
About 2 weeks ago, I read the governor in Puerto Rico is trying to they want to raise money to build a brand new one bigger than what they had. So hopefully they do that, but now that was governor. Now he's out now. Somebody else just came back in. So we'll see what happens.
Yeah.
Okay. I had one other question or comment.
Sure.
Okay. Yeah. It had to do with that antenna, the horn antenna. It looked like that was a homemade job that you made. It looked like it was made out of a fiberboard, insulating board with siding that you would have if the same type of fiberboard that you would put on your house. Is that what that was made out of?
Yep.
Okay.
It's aluminized, and you have to use real aluminum tape, because it has to be
Yes.
conductive. The whole thing has to be conductive. And it was based on something, if you read my article, it gives all the measurements and stuff, but it was based on an article written by a Harvard professor. He wanted to make a portable thing, and he built a horn, and he did it out of metal. I just tried this thing because in the real old days, back in the 80s, we used to make little horns out of this board, this aluminized board. And I figured, what the heck, I'll give it a shot. It's really light. I can just throw it in the car, not a problem,
It looked really good.
Yeah, it's a great little device. I mean,
Very good. One other comment about Jupiter. Back in the mid 90s, they had the Shoemaker Levy comet that hit Jupiter, and the ARRL wanted hams to listen to it. And, we put on 10 meters, 28 megahertz for you, 28 megahertz AM. And we sat there for I think every 40 minutes another piece was going to hit, and they said you would hear the difference from the regular noise. And I had a beam at the time. I pointed it toward Jupiter, and I could hear the difference, and there would be a difference in the sound when one of these pieces hit. But I recorded it, but when I played it back, it didn't sound as dramatic as when I was listening.
Oh yeah, that's always the case. I belong to ARRL too, and I set up too, and I heard it, but like you said, my recordings are garbage. It just didn't. I couldn't get it, but I could hear it. So yeah, it was a spectacular radio event, and it's too bad we didn't get more attention for that. There were a couple articles I read about it, but just a nothing. It's too bad. But I'm glad you got to hear it, because that's probably a once in a lifetime event. That's not going to happen again anytime soon. So, anything else?
Can I be heard?
Quick question. You mentioned SDR radios.
Yep.
Is there an HF radio that you recommend for new hams?
I haven't used many, so I'm not a good person to get a recommendation from. Probably somebody from your club would probably be better. I've only ever used the real cheapos, and so because I try and I'm an educator and I'm retired, so I want to see how far I can push things. So this is like the lowest cost I could possibly do to be able to do science. And so I don't know the good stuff very well. So, but I know there are lots of HF radios. I was looking at one from AirSpy that actually had a converter that would bring me down into VLF, which is very unusual. So I was looking at that for some of the stuff I want to play with. But other than that, I mean, there are lots of good ones out there, and they're not all that expensive. And I'll let you ask people in your own group, because I'm sure they probably know better than I do.
And we're having a virtual ham fest on Sunday, February 28th. There'll be a lot of vendors there and used equipment there, and you'll get a lot of input and a chance to buy something.
Perfect. Great, Harry.
I heard Lou enter our queue trying to ask a question. He was very, very faint. Maybe we could let Lou give a try.
Sure.
Go ahead, Lou.
See if it's working. Can you hear
Yes.
me?
Yeah.
Yes,
I
go
can.
ahead.
Okay, I was having trouble unmuting before. At Brooklyn Tech, we have a Super SID package that we were running until now. The place has been shut down for a while. The other thing is we have a Jove receiver kit that was handed over to our club from the physics department with no documentation. Can we get an update to fill in the blanks on that?
Sure. There's links on our website, and if you can't get it, just let me know. I've got copies of it. Harry has my email. Well, I can give it out. What the heck? It's WALLACE, Wallace FJ at Comcast.net. So Wallace FJ at Comcast.net. If you can't find it, Radio Jove does have a website, and if you go to the Sarah website, there is a link. I can't remember exactly where. Up at the top of the page, there are link things, and I think it's under projects. But like I said, if you can't find it, just let me know. I have a thumb drive with all kinds of stuff from Radio Jove, so I can send that to you.
It would be rather interesting to try and get these things working if we ever get back into the school.
Yeah, the Super SID right now, for the past couple of years, I don't know, there's been no SID activity, none. I mean, I have reported nothing. I do solar astronomy, taking images, and with a H alpha filter, I can see stuff happening on the sun, but radio wise, there's nothing. There was a couple of very small flares recently. So we're in the process of getting back there, but in a couple of years, it's going to be really active. And that's when you really want to make sure you got it going. But you can, like I said, you can check the sunrise and sunset. That's every day, no matter what. And you'll see that really clearly. And if you do have problems with SuperSID, there's a tremendous user group if you can't get help. And you're always welcome to contact me and I can get you in touch with somebody.
Yeah, we had it actually operating 2-3 years ago, and we did see some events.
Oh yeah. Yep.
Monitoring the same station in Maine.
Yep.
The Cutler antenna that you showed us is the submarine array, which some
Right.
of our members may remember we had a presentation about several months ago.
Oh, good. Yeah. It's a spectacular thing. Oh my gosh. And I guess they're working on it now. Or were working on it over the summer. It was out for about 3 months. And I think they were redoing the antenna.
Yeah, we had a presentation by someone who knew a whole lot about it, and
Yeah.
we had photos of how it was constructed and the relative size of things. It's just a monumentally enormous
massive,
installation.
massive. Yeah.
And what's really astonishing about it is that it's actually 2 of them side by side.
Yeah. Yeah. Well, they don't want a failure. You want to be able to contact nuclear subs, pretty carefully, so yeah, it's spectacular. It's phenomenally powerful too. It's the most powerful one, I think, in the world. Maybe, I don't think Russia has one as powerful, but I could be wrong.
I think it's a megawatt on each of the 2.
Oh yeah. 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 It's phenomenal. Yeah.
I'm just wondering, as we hams generally talk about resonance of an antenna, we don't generally think that the size of the antenna is the key criterion, because if you make something too long, it's not resonant anymore, and then it's going to be a weaker signal. But in astronomy and many other fields, it seems that the size is the most important thing. Just wonder if you can reconcile those 2 points of view.
Well, it depends on what kind of antenna you're talking about too, I guess. In radio astronomy, we don't generally use wire. We use parabolic dishes, horns, things like that. And so for those, the bigger the aperture, the better. You get more signal. You still want this specific, for a horn, you want the specific sizes for your height and width. Or else it won't be resonant. And for parabolic dishes, you can reflect any frequency, so it's not a problem. So the bigger, the better. You gather more signal. So it's basically that. There are very few people who use dipoles or anything like that. And for those, you do want resonant, frequencies. For my big VLF radio antenna, I use 400 feet, just because they're so low frequency that you can't make a resonant antenna. So you put as much stuff on there as you can and hope that it's close enough. And these signals are so massive, you could put a coat hanger on and you'd detect it. But so that's probably the difference. With hams, you're probably using Yagis and things like that. And sometimes we use that helix. Things like that. But most of the time, the professionals are using parabolic dishes or horns or things like that. And so size matters.
I would point out one thing that might clarify that a little bit.
Sure.
The horn is really a waveguide. And
Right.
so the dimensions are very critical to make it resonant. A parabolic antenna, the dish is not the antenna. The dish is a reflector that's reflecting the signals to the antenna, which in the case of Arecibo was inside that big structure that hung over the dish. That's, if you look at a dish antenna for satellite TV, there's the dish and then there's this little boxy thing that's on an arm. That's the actual antenna.
Yeah.
And that is resonant.
Yeah, you're right. And you saw that in my first radio telescope that I built. The little can had the little wire sticking up inside. That's the resonant piece. Very good. Thank you, Harry. I should have remembered that. By the way, the Arecibo did not come to a focus like that. It actually had it was a circular disc, which I have no idea why they did that. And so they had to use a wire to capture it. It didn't come to a point. So they had to use multiple receiver points along a wire. And so that whole structure was it was huge structure, had to be hung up there so that they could actually capture the signal.
Okay, thank you.
Bizarre design. Yeah, my pleasure. I'm going to have to sign off, I think. But please, if you have any other questions, feel free to contact me. Check out our website and that kind of stuff. I'd love it if you guys got into some radio astronomy and let me know what you're hearing and detecting and things like that. It would be great. I'd love that. So once again, it's Wallace, WALLACE, FJ at Comcast.net if you want to get hold of me. And you can always get hold of me through the Sarah website. I'm the education coordinator. So just hit education and you'll get me. All right. Well, I really appreciate you changing your schedule a little bit to accommodate me. And I hope this was worthwhile and that you guys will pursue this a little bit. And I appreciate the chance to talk to you. You have a